Today's lecture is going to be about divergence and curl. These two are vector operators that we operate on a vector field, and that's why today we are definitely going to need the vector field big F again. So the vector field big F is coming back for today's lecture. Alright, first of all, let's put some coordinates into this vector field. Let's have x, y, and also z. When you see x, y, z like this, you know right away that this is a vector field in three-dimensional space. So this one is definitely in 3D. If you want one in 2D, just take z out and only have x and y left. Now, when it comes to the concept of a vector field, it's all about the space, whether it's 2D or 3D. At each location in the space, you have a unique vector, a unique arrow right there. But when you move to another location, a different coordinate in the space, you are going to get a different vector, a different arrow. And if you keep working on this process, repeating it over and over again, moving to another location, get another arrow, moving to another location again, get another arrow again, you are going to end up with a field of vectors, field of arrows, and that's why we call it a vector field. Okay, so that is the general idea of a vector field. Now back to the new topics for today, and that is divergence and curls. As I told you, these two are vector operators. Now the question is, are there any other vector operators that we have learned or seen so far in this course up to now? Well, the answer to that is yes, we have seen and learned some, and we are talking about these ones right here. Additions between two vectors, like vector A plus vector B, that is a vector operator. Subtraction between two vectors, A minus B, or the products between two vectors. Now, when it comes to the products between two vectors, we have two types, dot products and cross products. Let's take a quick look into these two. We learned about this before the midterm exam. We had this A dot B, vector A dot vector B. As you can see here, this is an operation between two vectors, and that's why we call this dot product a vector operator. Okay, that is the first type of the product. Now let's take a look at the second type, which is A cross B. Now when it comes to the calculations of these two, I am not concerned. At this point, I am pretty sure that you guys know how to handle them. But there is one thing I would like to point it out to you, is that these two operators, dot product and cross product, are vector operators that have to be operated on two vectors or two vector fields. So as you can see here, dot product has to be operated on A and B, two of them. And same with the cross product, A and B. So these two are vector operators that have to work on two vector fields or vectors. Now that is the main difference when compared to the new operators that we are going to learn about today, the divergence and curls. Divergence and curls are vector operators that have to be performed or operated on just one vector field. Alright, main difference right here. Divergence and curl operated on one vector field, and that's why we only need this big F right here today in order to find the divergence and curl. Now, what is so important about these divergence and curl that we have to learn about it today? Divergence and curls can produce special quantities that tell us about the characteristics and the behaviors of the flow of the vectors in the space at any point P and its neighborhood. Alright, it's kind of long, right? So let's imagine all these arrows in the space, and we are talking about the flow of them. And this divergence and curl can tell us about the behaviors, the characters of the flow without us having to plot them. That is the main point. By computing the divergence and curl, we can tell about the flow without having to plot them. So let's write that down. I know it's long. So divergence and curl tell us about the characteristics and behaviors. Okay, first one, characteristics or the behaviors. of the flow of vectors. Of flow of vectors. When we talk about flow of vectors, it can't be just one single vector. We are talking about flow of them. So it's going to be a group of vectors somewhere. So flow of vectors right here is going to be a group of vectors. Alright, at any given point. Okay, at any given point, I'm going to say P. And let's put coordinate as x, y, z. If you work on 2D, then just only have x, y. And not just this point. It's the neighborhood around this point too, the surrounding of this point, and its neighborhood. Sorry about the space here. Okay, so P right here is any point in space. Point in space. And from now on, for neighborhood, I'm going to use NBD as a short form for that. Okay, much easier. Okay, back to this characteristics of flow of vectors at any point and its neighborhood. This divergence and curl can tell us about this without having to plot them. Okay, it's kind of hard to visualize that, right? Imagine that in your head. So let's take a look at some illustrations here. So let's try to work on this figure on the left hand side. Since this is in 2D, let's put 2D right here. I am going to pick a point in this this space. So what about it's going to be one right here, and I'm going to call this point P1 at xy. All right, and since we are interested in this point and its neighborhood, so let's create this ball around this point and consider this to be the neighborhood of this point. Right, this ball right here. This neighborhood is supposed to be small, but I make it big intentionally so that it's clear to you. Alright, this ball around this point P1 is going to be the neighborhood of P1. So this is NBD of P1. Alright, now talking about the flow of vectors, I told you that this is about a group of vectors somewhere in the space. Alright, and it's going to be near the point P. So we are talking about all the arrows inside this ball that we just created. So we are talking about all of them here. Flow of vectors inside the ball and also the ones on the boundaries. So maybe one right here. Let's spend some time to highlight them all so you see what's going on. So from now on, when it comes to the word flow of vectors, we are interested in all of these blue arrows. So this small one too, this going down, going up, right, tiny one, and also the ones on the boundaries. Maybe some around here. So all of them here. This is the flow of vectors at any point P and its neighborhood. And we want to know the characteristics, the behaviors of all of them without having to plot them, and divergence and curl can tell us about that. Alright, let's go into the details at the meaning of each one of them, the physical meanings. So let's start with the divergence. I am going to start with the formula for the divergence. It's going to be this. Divergence, diff, as a short form of that, diff of divergence of this vector field big F at any given point in the space is going to be equal to this formula. Del, which is the maybe a new sign to you. This is the upside down triangle. This one is called del. Alright, dot with the vector field big F. That is it. That is the formula for the divergence. We are going to go into the details of this formula later in the next slide. So for now, let's put a box around this. Okay, so that is the formula for the divergence. Now, when it comes to the physical meaning of the divergence, what kind of characteristics or the behaviors can this formula tell us about? It's going to be about the overall flow of vectors, whether they leave or enter the neighborhood of that point that you pick. So let's write that down. It's going to tell us how much, how much of the overall flow of vectors, okay, whether they leave or enter the neighborhood of the point that you picked. Whether they leave or enter the neighborhood of the point you pick, it's going to be any point P, X, Y, Z. So the keywords is right here. Divergence is all about leaving or entering the neighborhood. What does it mean? Leaving or entering vectors? That doesn't make sense. Maybe some of you are thinking like this. So let's take a look at this example right here. Let's pick a point in the space and let's monitor the leaving and entering of the vectors. So I'm going to pick this point, this one right here, and I'm going to call it P2. Okay, P2 of XY. All right. Of course, we are interested in this point and its neighborhood, so let's create this neighborhood around this point P2. So once again, this ball around P2, and we want to know about the characteristics of the flow of vectors, whether they leave or enter. So we are going to focus on the ones on the boundary, on the circumference of this neighborhood. So it's going to be this arrow. All right. Okay, let's highlight them all, every one that you can see on the boundary. Okay, this one is on the boundary. Okay, this one too. And also this one. And I'm going to put this one right here. So from this you can see it's quite obvious that all of these vectors are leaving the boundary, leaving the neighborhood. So this is the case one right here, leaving. So let's make a note that what you see right here is when the vectors, the overall flow of vectors are leaving the neighborhood. Leaving NBD of P2. Okay. So that is the first scenario. But if the directions of the arrows are the opposite, if they all are pointing in, then that can be considered as the flow of vectors are entering the neighborhood. Okay, so that is going to be the second scenario when all the arrows are pointing in. Okay, now for the first scenario, when most of the flow of the vectors are leaving, we are going to call this as expansion, like moving out. So first one right here, this can be considered as expansion of the vectors around this point P2. Expansion. Alright, or you can call it vectors are expanding around this point P2. But if the overall flow of vectors are entering the area, then we are going to consider this as contraction of the vectors. So this number 2 right here is going to be contraction. Contract means like moving in. All right, so contraction of the vector field. So divergence is all about these two words: expansion of the vectors or the contractions of the vectors, and that depends on the ones on the boundaries. Now that is the physical meaning of the divergence and what kind of characteristics it can tell you. Now let's move to curl. So let's start with the formula for the curl. It's going to be this: curl of vector field at any point in the space x, y, z equal to, once again we have this sign, new sign, del, cross with the vector field, big F. Alright, very similar to the divergence, except that we use cross product here. Okay, let's put a box around this once again. And I'm going to talk about this later in the next few slides. But for now, let's stick with the physical meaning of the curl and what kind of characteristics it can tell us. So this curl can tell us about how the flow of the vectors circulate around the neighborhood of this point that you picked. So let's write that down. It's going to tell us how the overall flow of vectors, once again, how these groups of how the group of vectors around this point P are going to circulate. All right, flow of vectors. Circulate. Keyword is right here. Circulate in the neighborhood of point P. Okay. Before, the keyword is about expansion. For the divergence, it's about expansion or contraction. But now it's about circulation for the curl. So right here we have this circulate. So it's going to be about circulation. That curl can tell us about the behaviors in the space. Okay, what does it mean by circulation in the space, in the vector field? Does it make sense? Well, at this point it might not, so let's take a look at this illustration right here, an example. So let's pick a point. I'm going to pick one right here. Let's call this point P3. X, Y, alright? And once again we have a neighborhood around this point P3. Okay, let me fix on this one. This neighborhood, make it a little bit bigger. Okay, and now we want to know about the circulation inside this neighborhood. We want to know if we put a turbine in this neighborhood, is it going to spin or not? And if it does, which direction is it going to circulate? So for this one, for the curl, we are interested in this. We want to know what's going to happen if we put this turbine. Alright, something like this. If we put a turbine right there, is it going to spin? Spin or not? And if it does, is it going to be clockwise or counterclockwise? Okay, CC or CCW, CW. Alright, so this one is supposed to be CW, clockwise or counterclockwise. So curl can tell you about that. Okay, so divergence, all about expansion or contraction. Curl is about circulation at any given point and the neighborhood of that point. Okay, so that is the main idea. Now let's move to the details of each one of them. Let's start with the divergence. So in this slide, we are going to work on the divergence. So why don't we start with the physical meaning again? Divergence can tell us about the overall vector, the flow of vectors around a point, whether they go in or they go out of the neighborhood. So let's write that down again. Overall flow of vectors. Alright, going in or going out more. Okay, two conditions here, going in, going out. Now, going in, this is entering, enter. Entering, it's contraction. Contraction. What about I put this in one line? First one is going to be enter. Going in, this is enter, and contraction. Alright, if the flow of vectors are going out, they are leaving. Leaving the area. Leaving, it means moving away. This is expanding. Expansion. Alright, that is the physical meaning of the divergence. Now, let's start with the formula. Okay, so formula, once again, I'm going to bring this back again. So it's going to be diff of any vector field big F x y z equal to del dot with the vector field itself big F x y z. Okay, so I know that this is new to you. We have seen this del before from the gradient, but we don't know about this in details. But this is the good chance right here. So once again, this is the formula that we have. Okay, so why don't we start with the vector field that we have right here is the big F. So let's write that down. We have this vector field big F, and since this is just a regular vector field, each component can be anything, can have any subfunction to explain it. X, Y, Z. Each component can have the freedom to be anything. So I'm going to put this subfunction M, all right, M of X, Y, Z to explain the component I. Subfunction N to explain the, oh, sorry, this is supposed to be plus. Subfunction N, X, Y, Z to explain the J component. And last component can be explained by P, X, Y, and Z. Alright, so F right here, just a regular vector field. M and P can be anything. Okay, now let's talk about this del. So let's use red. So this one is called del. This upside down triangle. So what is this? By its own, it has a formula. So let's take a look at the formula of this alone triangle upside down. It's going to be equal to, this one equal to partial derivative of something. Alright, this is a blank. With respect to x, first component, plus partial derivative first order of something, also blank right here, with respect to y, j component, and partial diff, first derivative, first order derivative of something with respect to z, and that is the last component. Well, this is the formula for del, and as you can see here, by itself is not complete because we still have all these blank spaces. Right? So del by itself, it has a formula, but it's not complete, and that's why we always use del with something. We always follow del with something, and we did that before. We had this del of f, which is the gradient of f. So when you put f right here, f is going to go into all these blank spaces. It's going to be this df by dx I plus df by dy j plus df by dz k. And this is the formula of the gradient of a function that you learned before the midterm. But it actually has a meaning by its own, this del thing. And it's going to be this one right here. You can make a box around this one. Okay? Now, that is del. Let's find out about the formula for the divergence, which is this, del dot f. Let's find out about this del dot f right here. So we are going to perform a dot product between del and the vector field big F. So we are going to find the product of each component and then add them together. So in the end, let's find the details of this formula of the divergence. So it's going to be this. Divergence, oh, okay, one black. Okay, divergence of a vector field big F at any given point is equal to del dot vector field x, y, z. Okay, this is dot product. I am going to find the product of each component. I'm going to start with the first component right here. I component, m, and this partial diff with respect to x. With these two, I am going to get this partial diff, first order of m, well, you know that this is xyz, so I'm going to leave xyz out with respect to x, first component. What about I put it right here, x, y, z. Okay, so partial diff of m with respect to x, that is the first component. And now I need to find the product of the second component, n and partial diff with respect to y. So that is the second component, second product, n partial diff of n xyz with respect to y. And last one, last component, the product of them, p and partial diff with respect to z. So I'm going to get this partial diff of p xyz with respect to z. Okay, this is one. This one is with respect to y. Dot product, you are supposed to add them all together. So there you go. That is the divergence of a vector field in details. That is the full formula that you are going to use later. So let's put a box around this. Okay, so there you go. When in terms of the calculations, you use this. So the question is, when you get the result, when you get the divergence, oh, by the way, this comes out to be a scalar, right? Keep in mind that this is scalar. As you can see here, there is no component ijk anymore. This is dot product. So this one, divergence is scalar. So what does this scalar tell us about the characteristic of the vector field? So let's take a look here. This is going to be categorized into the three cases. The first one is when divergence is positive. Second one is when the divergence is negative. What about this? When you've found divergence, you can check the sign of divergence, whether it's plus, minus, or 0. 3 cases. Alright, now let's start with the first one, when the divergence is positive. This one right here. So I'm going to put it right here. When divergence, when diff of f is positive, this condition is going to correspond to the flow of vectors that are going out of the neighborhood of a certain point. So this one is going to correspond to flow of vectors leaving, or in other words, we are talking about expansion. So if the calculation of the divergence comes out to be positive, you are going to get this behavior at that point that you perform the calculation on. Expansion. What kind of phenomenon you are going to see? You are going to get something like this. At this point P, and you find the divergence to be at this point, diff f to be positive, then you are going to get this kind of phenomenon. Most of the vectors are going out. Alright? Most of them going out. I'm not saying that all of them have to be going out. You can have some that go in, like this. Right? You can have some. But in the end, the overall, in general, the vectors are going out from this neighborhood. Okay? So once again, I want to stress on the overall. Overall are going out. Okay. But you can expect some to go in. Now, that is the first scenario. When the divergence is positive, you expect to have this expansion of the vector field. Second scenario is when the divergence is negative, and that is the second case right here. Divergence f is negative. When you get this calculation, it comes out to be -2, -3. You need to know that it corresponds to this flow of vectors overall are going in. Okay, flow of vectors entering the neighborhood. Once again, this is overall. What about I put one right here? This is about the overall in general. Alright, this is entering. It means that most of the vectors are going in. So we are talking about contraction of vector fields. Contraction. Okay, so that is the second case when the divergence is negative. So you should expect to see something like this. Most of the vectors are going in on the boundary. Right? Most of them going in, contracting to the neighborhood. Right, let's have some more. But you can expect some of them to go out, but not the majority of them. Just the minority can go out, maybe a few more. Alright, but as you can see, in the end, the overall flow of vectors are going in, and this is considered to be contraction of the vector field. Now, the last case is when the divergence comes out to be equal to 0, this one right here. So let's write that down in the middle of this page. When divergence of a vector field, big F, at any given point comes out to be equal to 0. So what does this mean, divergence equal to 0? As you might have expected, this is going to be the case when you have the same amount of vectors entering the neighborhood as they are leaving the neighborhood. So in the end, the overall flow of vectors will go in and out equally. So let's write that down. The overall flow of vectors go in and out equally. Alright, so when you have the same amount of vectors going in as they are going out, then this is going to be the case when you have neither expansion nor contraction. Nothing gets bigger and nothing gets smaller. So this one is going to correspond to neither expansion nor contraction. Neither expansion nor contraction. Alright, so that is it. When it comes to the calculation of the divergence, you just need to follow this formula down here. Just need to keep in mind that when it comes to divergence, it has to come out as a scalar, right? Never expect the divergence to come out to be a vector, and if it does, then something must be wrong in your calculation. It has to come out as scalar. Once it comes out as a number, then you need to do some interpretation. If you get a positive number, you need to realize that you are talking about a situation where the vector at that point is expanding. But if the divergence comes out to be negative, then you can visualize all the vectors are moving in, so you have a contraction. But if you get a number that is 0, then, well, the amount of vectors going out and in are equal, so it mostly stays the same. Alright, so that is pretty much everything you need to know about the divergence. Now let's move to curl in the next slide. Okay, curl, let's start with the physical meaning of this, and also the characteristics or the behaviors of the overall flow of vectors that we can expect curl to tell us. Okay, so let's start with that. Curl can tell us about the overall flow of vectors, how it circulates in the space or in the vector field. It can tell us how overall flow of vectors, and here is the key word, circulate. Okay, circulate at any point in vector field, big F, X, Y, Z. Okay, let's start with the formula for this curl. I'm going to write it down right here. It's going to be the same as what we had before. The curl of a vector field big F at any point in the space, let's put x, y, z in for now, is going to be equal to the cross product between del, so del is back again, cross with the vector field itself. Alright, so that is the main formula for curl. Let's put a box around this one. Now we are going to work on this formula and show the details of this. But before that, let's show all the components of del and the vector field big F. Let's start with the vector field big F. We have these components. F of x, y, z. Each component can be anything, so we can use this subfunction m x, y, z to explain the first component I. Same as what we had before. This one is going to be n. Right, this is supposed to be plus n of x, y, z. For j component and last component, we describe that by p subfunction x, y, z, k. Alright, so that is the components of the vector field F. Now let's take a look at the components of del. So before we had this del to be equal to, from the formula, first order partial derivative of something. So this is blank with respect to x, first component, plus partial derivative, first order of something with respect to y, second component j, and last component k, first order partial diff with respect to z. Okay, k hat right here. Once again, we have blanks or empty spaces following the partial derivative. It can be anything, depends on what follows the del right here. Okay, now we are going to perform the cross product between them, between del and big F. So let's do that right here. So it's going to be, what about I put this? Cross product between del and vector field F of x, y, z is going to be equal to, this is the formula we already know, so it's going to be equal to the determinant of this matrix. Okay, so determinant of this matrix right here. So let's put I, j, k at the top. I, j, and k. Alright, so let's start with the components of del. So we have partial diff of something with respect to x, partial diff of something with respect to y, and partial diff with respect of something with respect to z for the last component, and that is del. Now the components for the vector field is going to be m, n, and p. Alright, we have m, n, and p right here. Oh, not r, supposed to be p. And let's perform the, let's find the determinant of this matrix. So I'm going to put everything into components again, because we know that the cross product has to come out as a vector. This one must come out to be a vector, which means that curl has to be a vector. So keep this in mind. This curl right here has to be vector. This is different from divergence. Divergence is scalar, but curl is a vector. Okay, so in the end, we should expect to have a vector as the final result. So I'm going to put everything into components. So I component, j component, and k component. And each component must have some coefficient in front of them. Alright, this one for k. What about I fix this one to have a little bit more space? For j component, now let's start with the I component. So I'm going to take this path to get the I component. Take this one down, cross down. Alright, first path. Along this path, I'm going to get the first order partial derivative of p with respect to y. So, first order partial derivative of p with respect to y. Okay, now next one, cross down from j, in this path to here. Alright, along the second path, I'm going to get the first order partial derivative of m with respect to z. So it's going to go to here. First order partial diff of m with respect to z. Okay, now next one is going to be this path. K partial diff with respect to x and n. Okay, so let's write that down. It's going to be partial derivative of n with respect to x, right? Can't find it. Okay, so that is the positive terms that we have from the crossing down. Now we have to cross up. So let's cross up. Okay, so start with this I. I'm going to start with this one, crossing up in this path, so that I end up with the I component. And it's going to be partial derivative of n with respect to z. So let's write that down. Minus partial diff of n with respect to z. Now, second component, j. It's going to be along this path, p partial diff with respect to x and ends at j. This has to be negative, so minus partial diff of p with respect to x, j component. And last one, along this path, partial diff with respect to partial diff of m with respect to y. Partial diff of m with respect to y, k component. So we have the complete components of this curl. Since this is quite a lot of things going on, let's use the short form for each term like of this. So we are going to call this one py, right? P with respect to y, and this one n with respect to z, n sub z, and this one m with respect to z, this one p with respect to x, and this one is n with respect to x, and last one m with respect to y. Now let's put all of these together in one short formula down here. So it's going to be the complete formula for curl of f in 3-dimension xyz equal to, well, it's going to be del cross f again, and equal to all these terms. First component, py minus nz. Okay, I component, plus m sub z minus p sub x, j component, and last component, n sub x minus m sub y, k component. And that is the complete formula for curl. So let's put a box around this. Okay, all the way through to the right hand side, and same here. Now this is the complete formula for the curl. Something to keep in mind is that it has to come out to be a vector. Curl has to be a vector. This is the major difference between divergence and curl. Divergence is a scalar, but curl is a vector. Now, when it comes to the interpretation of the curl, it's going to be about the circulation or the rotation, and it's going to be based on the coefficient of the k component. So when it comes to the characteristics and the behaviors, we are going to determine by this coefficient right here. The reason that we are going to use this coefficient is because when it comes to rotation or circulation, we need a reference. We need to know how we look at the rotation. For example, when you look at a fan that is moving, that is spinning, you are going to see a certain direction, right? How it's going to spin. But if you look at the same fan from behind, from the back, you are going to see the same fan spin in the opposite direction of what you just saw at the front. And that is why we need a reference when it comes to circulation and rotation. And this coefficient right here in front of k is going to be that reference for us. Now, how is it going to work? Let's take a look here. We are going to, by the way, the reference that we are going to use here is called right hand rule. So it's going to be this right hand rule. So we are going to follow this rule in order to determine the circulation and the direction of the rotation. So what about we try to have one example here? For example, we have a thumb up, all right? It's like a like in Facebook or something. So let's have a thumb up. So it should look something like this. Okay. Okay, I'm trying my best to have this nice thumb up. So something like this. Okay, not so good. Let me change that. Okay, this is better. Okay, so we have this thumb up. And we are going to use this thumb that we have right here as the reference of the rotation. So it's going to be this direction. And it's going to correspond to this positive k right here. So what we have right here is a positive k direction as the reference. And let's follow your fingers for the rotation. If you follow your fingers, it's going to wrap your hand in this direction. Alright, and what you see right here is a circulation in counterclockwise direction. So what you see right here, counterclockwise. And this is going to correspond to the rotation of a turbine like this, counterclockwise. Okay, and this follows from the right hand rule with the reference as the positive k. So the key is right here, positive k. And you get the counterclockwise rotation. So that is the first scenario. When k component, what about I use red? So here we have k component comp of the curl is positive. For this one, you get counterclockwise rotation. So this is going to be counterclockwise. Okay, let me change that. Okay, counterclockwise. Okay, that is first scenario. Number one, k component, the coefficient greater than 0, positive. Now, when the k component is negative, you are going to get something different. You are going to get a thumb down. So let's write that right here. So it's going to be something like this. Okay, thumb down. Okay, we have thumb right here. So thumb down is going to go into the direction of negative k, minus k hat. So we have this direction as the reference, going down minus k. In this direction, you are going to follow your fingers, and you are going to see the circulation in the direction of clockwise. It's going to wrap your hand in this direction. So it's going to be clockwise rotation. So if you use this as the reference, minus k, you are going to get this clockwise rotation for the turbine along the vector field. So this one is going to correspond to when the case when k component, k comp of the curl is less than 0. So for this one, for this case, you expect to have clockwise rotation. Clockwise. Okay, and that is the second scenario that we have when it comes to the value of the curl, the k component. K component less than 0. K comp of the curl is negative, less than 0. And of course we have the last scenario when the k component is equal to 0. Let's put it in the middle. K component equal to 0. And of course, this is going to correspond to the case when there is no rotation. Right? So this is going to be no rotation for the last scenario. Okay, last one, k comp of the curl is equal to 0. So there you go. We have all the three cases. When it comes to the calculation, just follow this formula. And once you get the result, just check the coefficient of the k component, and you can determine whether it's counterclockwise or clockwise or no rotation at all. And that is it about the curls that you need to know.